Hello and welcome. We're at the top of the hour, so we'll go ahead and get started with our webinar. My name is Melanie, and I'll be your facilitator for the webinar today. Our presenter is Randy Long. Thank you for joining ANAB for our complimentary webinar on what is metrology. Please note that we are recording this webinar, so it will be available for viewing in the future. Just a couple of logistics before we get started. Due to the number of attendants, everyone will remain muted for the duration of the webinar. If you have any questions as Randy is presenting, please enter those questions into the Q&A box. We have planned time at the end of the webinar to answer any questions that you may have. Also, we like to go over our disclaimer before we present our webinar today. The content delivered today is not guaranteed to fully prepare you for any specific application for accreditation. Attendees are responsible for determining the applicability of the information presented to your specific circumstances. Any examples that are provided today are for illustrative purposes only and are meant to facilitate your understanding of the concepts that are discussed. They're not to be interpreted as templates, prescriptive models, or representations of compliance with any specific standard. Before I pass the ball over to Randy, I'd like to introduce him. Randy enlisted in the U.S. Navy in November of 1983, opting for accelerated training in the aviation electronics field, after which he was assigned to the U.S. Navy's Advanced Electrical and Electronic Measurements and Microwave Measurements Calibration Schools in Denver, Colorado in December of 1985. Upon graduating at the top of his class, he immediately started his calibration career in a one-man laboratory in Christchurch, New Zealand, where he learned the hard way by breaking out the books. His lab earned 3 consecutive Outstanding Activity Awards during his 2.5-year assignment there. Randy worked in several commercial and manufacturing calibration labs before joining ANAB, or the ANSI National Accreditation Board, as an accreditation manager for calibration laboratories and EMC testing laboratories, as well as inspection bodies, where his duties consist of assessment team allocation, assessment package review, assessor evaluation and training, laboratory assessment, internal auditing, and participation in the Accreditation Council. He's undergone 17011 training and has taken on responsibilities for APAC and IAAC peer evaluations of other accreditation bodies. Randy participates in several standard development organizations as well, including NCSL, ASME, ASTM, C63, and SAE. He's also a member of the board of directors of the Mishawaka Historical Museum in Northwest Indiana, founded by his mentor, Don Herman. With that, Randy, I'm going to pass the ball over to you.
Well, good afternoon, good day, wherever you are. Thank you for attending this webinar on what is metrology. First, metrology is quite simply the science of measurement. It has nothing to do with weather, except there's lots of measurements in weather. We're going to talk about metrology in everyday life, metrology in business, metrology in industry, and then a little bit about traceability and uncertainty. First, metrology in everyday life. We practice metrology, or we do measurements every day, and even in early life, there are a number of measurements that folks make. If you look at children, they measure all sorts of things. You know, one, their age. It's like you see a little girl there, she's 3 years old. Sometimes you ask a child how old they are, and they hold up 3 fingers and say, I am this many. Or they'll say something like, my birthday is in 2 weeks, measuring time. Quite often, a small child might say that this food is too hot. So there's a measurement of temperature there. And of course, they're all proud of how tall they get. Or they talk about measuring currency, money. I have $5 and I need 2 more to buy this toy. slightly more advanced than the three fingers. Metrology in everyday life. Well, there's the old bathroom scale, what we're all fond of. When I go to the doctor's office, I said, what did the liar say today? So we use that to monitor weight, weight management, weight loss, weight gain, whatever we need. Another example of metrology in everyday life is in the kitchen. We might weigh ingredients. We might portion out quantity values of flour, sugar, things like that. Of course, spices and temperature. And then there's the metrology on the way to work. We monitor the speedometer in the car to see how fast we're going. We might do some risk analysis to how fast we are going compared to the speed limit signs. Or we might wonder how fast someone else is going. Another way we use metrology in everyday life is in our finances. We measure money as far as our savings, our investments. We look at our budget and we decide what quantity of money is going to go to entertainment, what quantity of money is going to go to food, how much goes to the various utilities, or even the mortgage. And if you do any flying or anything like that, they're going to weigh your luggage so that they can support safe flights. Metrology in business, slightly different. Counting, inventory counts are a measurement of how many parts you have, how many goods you have to sell, or you might use inventory to decide how much inventory you need to buy. Of course, in business, we look at profits and losses. You don't want too many losses, and in some cases, you don't want too many profits, although we usually like lots of profits. We also measure successes and failures to find trends. You can think of an automotive line where it looks, let's say, making airbags. Some of those are tested, but you're looking at failures or productivity charts. And then metrology supports quality across industries. So metrology in industry. Well, there's metrology in testing. Accreditation supports the accuracy of those measurements and the reliability of those products. Absolutely everything is tested. The size of a journal on a camshaft, the strength of the steel. Color is a very important one. If you look at a vehicle, there's lots of different colors out there, and then different materials have different colors, and those are measured against each other so that you don't get clashing blues on your car and your dashboard. Temperature is another one. Temperature of heat treating of metals, temperature of fluids, temperature of exhaust temperatures, let's say. Another thing is measured are output characteristics of devices. You might have a signal generator, so the output frequency would be measured, the output level, the noise on that signal are examples of output characteristics. And of course, we have chemical characteristics. Some of the more common ones are maybe pH or conductivity of cleaning solutions used in industry, or even the chemicals themselves used for testing other types of equipment. So metrology and testing, which supports all that stuff. Metrology and product certification. So at ANAB, we accredit product certification bodies as well. So before an item comes to market, let's say in the United States, let's say a cell phone, for instance, There's lots of testing that goes on that cell phone, signal strength, signal sensitivities, how much power it radiates, how that power affects the human body itself. All these test reports, accredited test reports, support the confidence that that equipment meets all the requirements it was designed to meet. Again, on product certification, there are lots of different schemes to qualify instruments. The Energy Star is a program that most people are familiar with. So when you see that something is going to cost you X number of dollars a year to operate, that was determined through long-term testing to determine the amount of energy used. FCC, Federal Communications Commission, cell phones, for instance, are certified instruments to FCC requirements. CPSC is another fun one. This is the Consumer Product Safety Commission, and these deal with the safety of items in the home. Make sure that small hands don't get pinched between pieces of, between a door and a case of, let's say, a dishwasher. Of course, there's lots of testing done on toys. It might be mechanical testing like that, or it could be determining how much, what kind of materials are in plastics, for instance. Lead's a big one that people are very concerned about in toys. And then these certification packages rely on the testing data to confirm it meets all those design requirements as part of the duties of a product certification. So metrology and logistics, credit calibration support quantities, weights, etc. If you're going to ship a quantity of plastic to an injection molding company, you need to know the weight of that plastic so that it gets shipped properly. The bill of lading on the truck is proper, or just counts of parts going into things, usually done by weight. Then we get to traceability and measurement uncertainty. Traceability comes in two flavors. You have traceability of materials. So if, let's say, we take the example of the plastic has to meet its requirements, but when sampling amount of plastic to do some testing, you have to know which lot it came from or which run it came from. Lots of different types of lot testing, could be chemical, could be all sorts of things. And then there's metrological traceability. And this is the traceability of the measurements made during the testing phase or calibration phase of these measurement processes. And then measurement uncertainty. Quite simply, it's the uncertainty of measurement is an estimate which quantifies what we do not know about a measurement result. And it's always an estimate, and it's usually expressed at a confidence level of 95% so that we know that our measurements are reliable. For metrological traceability, those measurements must include the uncertainty of measurement. And I went through my slides very quickly.
All right, well, thank you, Randy. I'm going to go ahead and take control back. That's what Randy had prepared to present today, and in order to give you some time to ask your questions, I'm going to go over some additional resources that ANAB has for you in your journey to accreditation, or for if your laboratory is accredited. We offer webcasts on our website. These webcasts are on a variety of different topics. They're about 5 to 20 minutes long, and they're free to watch at any time. You can go to our website and find free resources, and that's where our webcasts will be. We also have a blog page that has a wealth of information on accreditation and accreditation-related topics such as risk, standard requirements, internal auditing, and many other topics. We also provide these webinars monthly. In conjunction with this webinar today on what is metrology, we are hosting a webinar next month on in-house calibrations for testing laboratories. That will be posted on our website within the next week, so keep an eye out for that. We also offer a lot of training in a variety of different areas. Randy touched on a couple of those today. You know, the testing laboratories, calibration laboratories. We also offer training for product testing or product certification bodies as well, and many other topics like internal auditing, method validation, measurement uncertainty, and measurement traceability. A lot of our trainings are live online or self-paced, and you can find all of these resources on our website at anab.ansi.org. Now we are going to go into the questions that have been asked. I do have a couple of questions here, Randy. The first one is, I heard you define metrology, but could you redefine it for me? And what is metrology? The question asks, I thought metrology was calibration, but it sounds like metrology is more than just calibration.
So I gave a general description of what metrology is. I didn't provide an actual definition. There's actually a free document called the International Vocabulary of Metrology. It's got a long, drawn-out definition of metrology. But yes, metrology is more than just calibration. Metrology is that science of measurement, and measurements are happening everywhere. In testing laboratories, in inspection bodies, in proficiency test providers, in factories, in daily life. Metrology is everywhere. So the metrology is the study of measurement in general.
All right, the next question, how does metrology translate to my equipment?
Depends on what kind of equipment we're talking about. If we're talking about test equipment used in a calibration laboratory, metrology or the calibration of that equipment is critical for the work that it's going to perform. You purchase a piece of equipment to meet a certain need, and you need to ensure that those measurements this equipment is making is doing it to the degree that you want it to, or to the accuracy you need it to. In a testing laboratory, let's say you're an engine builder. So you're going to test this engine, and you're going to measure output gases, you're going to measure temperatures, you're going to measure speeds, you're going to measure power on a dynamometer or something like that. So all that equipment needs to be calibrated, and that's where metrology comes in, not just the calibration, but the testing itself and the test results, the resultant data.
All right, the next question is, what's the best way to approach an uncertainty budget?
The best way to approach an uncertainty budget, in my opinion, as I do assessments, but I used to run laboratories. I used to work in laboratories, calibration and testing. The best place to start with an uncertainty budget, in my opinion, is to start with the procedure. The procedure is going to tell you what measurements are being made. So you start there. You identify your reference standards that you're going to use for a particular measurement. You need to know its long-term stability. You need to know, how much it's going to drift between calibrations, let's say, what its accuracy is, the resolution of the reading itself, any environmental conditions, the reproducibility of multiple people making the measurements, the repeatability of the equipment making the measurements short term. And then you combine all these things using probability distributions. That's a whole nother discussion. Basically bringing everything to one standard deviation. You then square those, you sum them, and then you take the square root, and then you multiply it by a coverage factor to get the confidence level you're looking for in that end result. So I would start with the procedure. One thing I've found over the years is the average technician may not be calculating uncertainties, but they instinctively know where the weak points in a measurement process are. They know where, just instinctively, the difficult parts of the measurement equation. So yes, the procedure gets you a measurement equation, gets you your contributors for the uncertainty budget, and then you can do the math.
The next question is, what are requirements from ISO 17025 or from it says 17025 accreditation for laboratory developed methods?
So laboratory developed methods, that's a method validation. That's a whole nother topic. Generally speaking, you want to find a measurement method that's acceptable to industry. And standards development, mentioned I've involved in several standards development organizations. In those meetings, we discuss measurements. We discuss what the measurement entails, what the measurement is trying to determine as far as the characteristics of the instrument. But in some cases, well, in many cases, a laboratory developed method is going to reference one of these reference standard documents and try to emulate that. And then a validation process to confirm that you can actually get the desired results. In other cases, you may not have a consensus standard out there, so you need to develop engineering process to determine what quantities you want to measure, how well you want to measure those, the accuracies that you're trying to achieve, and with low enough uncertainties to actually do a decent job. That's really a whole nother topic, method validation.
Right, and we do have pre-recorded webinars on method validation as well, so check out our website on that. The next question, how often should instruments be calibrated and what factors determine this?
Generally speaking, a manufacturer of an instrument will have done tests to determine the reliability of an instrument. But the user of the instrument, based on the risk associated with those measurements, is responsible for determining the interval between calibrations. If you were doing let's say, impact testing for vehicles, and you had instruments that were subjected to large forces or sudden forces, sudden accelerations, decelerations, you might calibrate those more often. If you have a device that sits on a shelf and outputs a particular voltage 24 hours a day, 7 days a week, and you've got proven stability over the course of years, you may calibrate it less often. Many companies will just default to a 1-year interval on equipment because it's easy to budget, but that's not necessarily a risk-based decision. But in some cases, you want to, based on the measurement and the risk of that measurement and what it's affecting, determine intervals based on that. Another way to determine intervals is the reliability of the equipment. If you know you have a piece of equipment that's, let's say, maybe getting older, or it tends to drift over time, and you can kind of predict that drift, and you can use that knowledge and that data to either lengthen or shorten an interval. There is no one answer.
We had a kind of a follow-up question, which you touched on a little bit there, but I want to go ahead and ask the question and let you provide the answer is how long can I extend the validity of calibration?
Basically the same process. You look at the risk of the measurement, typically, and the reliability of the device over its life, to determine if you're willing to accept that risk of it going out of specification or drifting too far for your measurement process. I recall I had some proving rings, force proving rings that were very, very reliable. And I have absolutely no qualms based on its performance over 20 or so years that if I needed to extend it a month or two, it was not going to be a risk. On the other hand, I had torque transducers that were used a lot, and a couple of them tended to drift more than others. So those I would not have extended based on the level of risk associated with the measurement. Again, there's no one answer for that. It's a risk-based decision based on your equipment and your measurement needs.
All right, the next question changes gears just a little bit. What is the impact of impartiality in legal metrology?
That's a really good question. Impartiality. So I've seen technicians get really upset when a measurement result is out of tolerance. Let's say in a calibration laboratory, someone sends in a piece of equipment and the technician determines out of tolerance and redoes the measurement several times. And what I used to tell my own technicians was that the measurement is none of your business. You're here to do the measurement. If you need to double check yourself, that's fine. The impact of an out of tolerance is the customer's business. So in that sense, a calibration laboratory has to be impartial. Just produce the measurement result and move on to the next step. The decision being taken is the customer's decision. So I think impartiality is very important in calibration. Likewise with testing. If you're, let's say, in a laboratory, in a testing organization, and you determine that something is out of specification, as a test technician, whether it's in or out is really not your concern. It's you to hand it back to the operator that, let's say, machined that part, or you send it to an engineer to determine the risk associated with how far it's out. Let's say in the dimensional world, you get some little room to wiggle as long as it fits, and that's a job of an engineer to do outside of the testing or the calibration operation. So again, like accreditation, we are impartial, a third party impartial. A laboratory technician must be impartial to produce good, accurate results that people can use.
The last question, oh, actually, there's a couple more that just popped up, but the next question is, was it a rule of thumb to always convert the measurement result to SI unit?
That's a common practice, but if I had a torque wrench that was in foot-pounds, I wouldn't want results in Newton meters because I can't read that on the instrument. Usually the customer determines if they want it converted into something else. The result should relate to the instrument in a way that's easily interpreted. Again, if I had a torque wrench in foot-pounds, I wouldn't want results in Newton meters or kilogram foot per centimeter or something silly like that. So that's between you and your customer, I suppose.
The next question, it says, you notice a drift in a temperature sensor. How would you address it?
Well, there are a couple of ways of addressing that. One would be, let's say we're an electronic thermometer, you might shorten its calibration intervals so that adjustments keep it within the range of accuracy that you need for your measurement process. Sometimes it's an exercise of this equipment is getting old and the electronics are aging and it might need repair. Might just need the power supply capacitors. You know, I'm old school repair guy. Might just need to replace the capacitor so that it regulates the voltage properly. It may be that equipment is 20 years old and maybe it's just time to replace it. So there's several different ways of addressing that. Again, based on your measurements and your risk tolerance.
All right, the next question. We've got several coming in. This is great. I would like to know how to perform the intermediate verification of calibrated equipment, and if it is necessary that the personnel who will perform it must be certified with some standard.
Second part first, there's no requirement to certify folks doing intermediate checks within an organization. Whatever training programs you have within your organization, you qualify your people the way you need to. As far as how to do intermediate checks, again, it depends on the risks of the measurements. And how often you do intermediate checks is again based on risk. You might not need to do a full calibration on a piece of equipment to do the intermediate check, but maybe pick some points that are let's say more sensitive areas within your measurement processes.
All right, the next question, on which type of equipment is intermediate verification of laboratory equipment allowed?
You can do intermediate checks on any piece of equipment you have. It's not a question of allowance, it's a question of your risk tolerance level for your measurement processes. I had in one laboratory I ran, I had a multifunction calibrator, a meter calibrator, that I would run hundreds of meters across it a month, many thousands in the course of a year. So my intermediate check frequency was once per month, rather than, let's say, halfway through a calibration interval at 6 months. In the system I had, I could run a reverse traceability report and find every piece of equipment that meter calibrator influenced the measurements on. And I was willing to recall a couple hundred customer instruments. I was not willing to look at 1,000. So if my meter calibrator drifted slightly, I could recall that month's worth of work and determine, based on my intermediate check data, what equipment might have been affected, and then issue recall letters to my customers to send it in for a calibration after I adjusted the thing or had it repaired. So it depends on the risk tolerance for your measurement process, how often you would do intermediate checks.
Our next question is, if your digital reference thermometer is calibrated in Celsius and you have a liquid and gas thermometer in Fahrenheit, can I use the reference thermometer that is calibrated only in Celsius and not in Fahrenheit?
I think I understand your question. Reference thermometers, often you can toggle them between different engineering units, whether it's Celsius, Kelvin, Fahrenheit. If it's calibrated on one scale, you're just changing engineering unit. The curve really doesn't change for the thermometer. It's just an engineering unit that the display is putting out. This is common, let's say, in force measurements. You have a load cell that's calibrated in pounds force. It's just a toggle or a menu setting to switch it to newtons. It's not considered uncalibrated at that other range, unless it's using different circuitry, which is not typically the case.
Okay, the next question. Which interpolation technique is best for deadweight testers?
Well, that's a good question too. The masses used for a deadweight tester should all be the same class. Let's say ASTM class 1 or class 2. If you had, let's say, mixed sets and you had a couple class 1 masses, some class 2 masses, some class 4 masses, you would not want to try to interpolate that data because essentially you're establishing different ranges of measurement because of the classes of the masses used. On a deadweight tester, you may have more than one piston, so each piston would be its own range as well. If you have the same class masses and a single piston, then it's a pretty easy thing to interpolate. Most common would be a linear interpolation based on at least 3 data points to confirm linearity. But in some cases, you might want to do several more points and do a polynomial curve if you see that the data is not linear. Again, depends on the instrumentation.
All right, then the last question that we have currently is it okay to express the uncertainty of measurement in scientific notation?
Yes. Some of our scopes of accreditation have uncertainties in scientific notation. Many do not. It's not a problem as long as it can be understood by the user, then it should be fine. Back to the topic of interpolation. There's a guidance document on our website I wrote years ago on interpolation, extrapolation, and calibration data, if you want to learn a little bit more about that. And you didn't mention it, Melanie, we've got several guidance documents on our website.
That is a good point, and I should add it to that slide for resources. All right, well, thank you all for your questions. That was very good presentation, Randy, and great questions from the audience. We really appreciate you coming to present for us today. I will leave you all with some contact information if you have additional questions about the webinar or the content of the webinar. You can email either training@anab.org or anab@anab.org. We appreciate you coming to listen to this webinar. And again, Randy, thank you so much for presenting for us.
My pleasure.